Today we're going to talk about polynomial functions and their end behavior. The end behavior of a function describes how a function behaves as it moves infinitely to the right and the left. In other words, the end behavior is what happens to the values of f of x, or y, as x increases or decreases without bound. You have been finding the end behavior for quite some time now. You did it in Algebra 2, but you may not have used the words increase or decrease without bound. Instead, you probably talked about the x values approaching negative infinity and the y values approaching positive infinity. Something else that might be different is that we are going to use this limit notation that you see here at the bottom of the page. Previously, you did write x with an arrow and you told whether it was going to negative infinity or positive infinity. The left end would go to negative and the right to positive. Now we're going to add this limit notation. So let's look at an example. Describe the end behavior of the following polynomials verbally and using limit notation. I'm going to demonstrate on the first one, and then I would like you to think about how you would do it on the second. This first graph represents an odd degree function. How do I know that? The ends are going in opposite directions. So let's talk about the left. On the left-hand side, I see this arrow. So, as the x values decrease without bound, my y values are increasing without bound. Now I will go to the right-hand side. As the x values increase without bound, the y values decrease without bound. Let's look at how it's written. You can see here how they wrote the left behavior limit statement. We're simply saying that the limit of the function is equal to positive infinity. Because if you remember, this is describing what is happening with the y values. On the right-hand side, we're saying that the limit of the function is equal to negative infinity. Because again, that is where the y values are headed. Take a second and see if you can describe the graph on the right. This graph has an even degree. Notice that both ends are headed in the same direction. Okay, so let's talk about the left. As the x values decrease without bound, the y values increase without bound. And on the right, as the x values increase without bound, the y values increase without bound. You can see the limit statements here and at the bottom of the page. In this next example, you do not have to be as detailed. We aren't going to use limit notation. We are just simply going to talk about where the graph is headed on the left and where is it headed on the right. So I do want you to think about two things: the degree of the function and the lead coefficient. Remember, if the degree is odd, it's going to behave like a line. A positive line will climb and a negative line will fall. If the degree is even, it's going to behave like a parabola. A positive parabola will have both ends up. A negative parabola would be both ends down. All right, in A, I have a positive odd function. So it will be a line that climbs, which means the left side of the graph will be going to negative infinity and the right side to positive infinity. In B, I have an even positive lead coefficient. So both ends will be going up. Both the left and the right will approach positive infinity. In C, it's an even degree with a negative lead coefficient, so both ends will be going down. Both the left and the right will be headed to negative infinity. All right, take a second. You look at D, E, and F and see if you can determine what the ends are going to be doing. So I hope you remembered on D and on E that sometimes you do need to put your polynomial into the correct order. The lead term is negative x to the fifth, which means the degree of the function is odd and it has a negative lead coefficient. So in this case, it would be like a line that falls. It would be positive infinity on the left and negative infinity on the right. E is the same. It is out of order. The lead term is this last term. So we have an odd degree with a negative lead coefficient. Positive on the left, negative infinity on the right. In this last polynomial, you would actually have to think about if you multiplied your x terms together, what your lead coefficient would be. Once you did the multiplication, you would end up with x to the third power as your degree of your polynomial. As far as whether or not it was positive or negative, you do want to look at your x terms. You can see I've got a positive, and a negative. So I would end up with a negative lead coefficient. Therefore, it's going to be like a line that falls. Positive on the left, negative on the right. So now I just want to talk to you about what your homework is going to look like. In these first 8 problems, they do want you to write out your limit statements. So just like we demonstrated before, you don't have to write all the verbal statement. You just need to write the limit statement showing the end behavior for each function. In the next group of problems, you're going to determine the end behavior. You can do this the same way as the examples we just completed. Just simply tell where is the left side of the graph headed and where is the right side headed. And then finally, you're going to have a matching exercise. For this first limit statement, you are supposed to pick the appropriate function that would match it and the graph that would match it. You'll write these down here at the bottom, and then you'll go to limit statement number 2.